All right, number one. Here are 4 descriptions of the velocity of a hockey puck in the xy plane, all in meters per second. For each description, determine whether the x and y components of the acceleration are constant and whether the acceleration vector A is constant. And then it also asks for what the units would be for that last one. All right, so let's do 1 here. I mean, once you get through, nothing else has a higher exponent than a squared in there. So these are velocities. How would you figure out the accelerations? Do the derivative. So what is the derivative of the x component, number 1? Great. What about y? Okay. So, is the x component's acceleration constant?
That one, yes. Or is that one, no, that one's yes.
Okay, you're right. One's different, one's the same. When I say the acceleration is a constant value, meaning as time goes on for some object that's moving and accelerating, as time goes on, it doesn't have a different rate of acceleration. It's a set rate. Is this going to be a set number? No, because it's based off of time. Okay, so the x component is not constant. How about the y component? Yes. Now, what about the overall? So, you have your x here, your y, whatever. That's your overall. Is your overall constant if one of the components isn't? No. As soon as one component isn't constant, then the overall isn't either. So bearing that in mind, number 2, which component is not constant?
The y.
Yeah, y wouldn't be constant, so the overall wouldn't be. How about number 3?
The I.
Yeah, the I, which is what? X, good. So that's not constant, so the overall is not. And then how about 4?
They're both constant.
Good, they're both constant. In fact, the y component of number 4 is specifically what? 0. But you would still call that a constant. It just isn't any y component. All right, and then they also ask you the units question. So this was number 4. If the velocity is in meters per second, times in seconds, and this was your velocity function, Thomas, what must be the unit that goes along with this 2 so that your velocity is meters per second? Okay, the 2 is seconds. So what times that is going to give you meters per second? If it was just meters, it'd be meters seconds, not meters per second. Well, you need a meters. That is correct. This is what I want to end up with. So what's got to go on the bottom? Erica?
Second square.
Yeah. Does that make sense? Okay, what about over here? There isn't anything to even multiply by at all. So the unit with the 3 would have to be what? Yeah, meters per second. Okay. Okay, that one wasn't even really a projectile problem anyway. Okay, number 2. Tyler. All right, so as the picture below shows 3 situations in which identical projectiles are launched from the ground at the same levels, at identical speeds and angles. The projectiles do not land on the same terrain, however. Rank the situations according to the final speeds of the projectiles just before they land, greatest first. So, which one's going to hit the ground and go in the fastest? A. Then what? And then what? C. Okay. Any explanation of that one? The farther down it travels, the faster it's going to go. Acceleration speeds things up as it's going down. Great, Tyler. Brandon, you got number 3. At what point in the path of a projectile is the speed A at a minimum and B at a maximum?
The minimum would be, I guess, at the apex.
Yep, at the peak. And the maximum would be?
Right before it hit the ground.
Or
right as you.
Good. Right as you released it or right as it hit the ground, assuming those were the same heights. Perfect. All right, number 5, Erica. Okay, you are to launch a rocket. What? Excuse me. 4. At a certain instant, a fly ball has velocity of v equals 25I minus 4.9j. X is horizontal, y is upward, v is meters per second. Has the ball passed the highest point of its trajectory?
I guess the highest point is when velocity equals 0, so then you just solve it with 0.
Well, you're correct. The highest point would be where the vertical component would equal 0. So looking at that vertical component, you should be able to tell if it's before or after that. If it were 25I plus 0, that'd be the peak.
Okay, so then it's past it.
Very good. So since it's minus 4.9j, that means the ball is going back down, so it has to be after the peak. Does that make sense? Okay. All right, number 5. Wes, you get to launch the rocket. All right, 5. You are to launch a rocket from just above the ground with one of the following initial velocity vectors. And they are all combinations of, x is 20, y is 70, but you got a bunch of different negative signs in there. In your coordinate system, x is horizontal, y is vertical. A, rank the vectors according to the launch speed of the projectile greatest first. What do you think would be launched the fastest?
They all kind of do the same.
Hooray! They would all be the same. Because you got your x component and your y component, you're really just doing Pythagorean theorem anyway to find the overall launch speed. So it doesn't matter which way they're going. They'd all be the same. All right, great. Part B, 2, Wes. Rank the vectors according to the flight time. Which one's going to be in the air the longest? Would it matter, Wes, if we launched one left or right? No, that shouldn't matter.
So probably 1 and 2 is the longest, and 3 and 4 are shorter.
Exactly. 3 and 4, you're launching them into the ground. They're angled down. I don't know why you would do that, but 1 and 2 would obviously be the longest. What?
He said it was more creative.
Emily has number 6. All right, number 6, a snowball is thrown from ground level by someone in a hole. So it literally is coming off the ground level. With an initial speed of v naught at an angle of 45 degrees relative to the level ground, on which the snowball later lands. If the launch angle is increased, do the range or flight time increase, decrease, or stay the same?
The range would decrease.
Good. The range would decrease. You're at 45 degrees. We talked about that yesterday. That is your max angle for your max range, assuming it's all level. Different story if you've chopped away some of the ground. So if you're angling it up, it may go higher, but it's not going to go farther down range. So how about flight time, though?
Stay the same. If it goes up higher,
Yes. Because you have some certain initial launch speed, whatever it is. If it's at 45 degrees, your components are the same. as soon as you start increasing the angle, it's still the same hypotenuse, still the same launch speed, but your vertical component would have to grow and your horizontal component would decrease to keep it all the same. So the steeper the angle, the farther up it's going to go, and the shorter downrange is going to go, and the longer it would be in the air. All right, Daniel, you got number 7. I don't know why we switched from a snowball to a mud ball, but a mud ball is launched 2 meters above the ground with initial velocity v0 equals 2I plus 4j. What is its velocity just before it lands on the surface? That is also 2 meters above the ground. It's landing the same level at which it was launched. So just imagine it was launched at ground level, landing on ground level. They've given you the initial launch speed. You know projectiles are symmetrical. So what would the final speed be?
2I minus 4j.
Perfect. 2I minus 4j. All right, good. 2 more.
Yeah, in calculus yesterday, we actually learned that there is a derivative of acceleration that you can use.
You can use?
Yeah.
What's its physical meaning?
Here, I'll get mine at the salad.
Well, I mean, you could do it, but if it...
It's used to show like sudden changes in acceleration.
Okay.
Notes are actually below.
Sure. Bring those later. Okay. All right, Zach, you got number 8. All right, an airplane flying horizontally at a constant speed of 350 kilometers per hour over level ground releases a bundle of food supplies. Ignore the effect of air on the bundle. What are the bundle's initial vertical and horizontal components of velocity?
Alright, so the spot horizontally. I guess the vertical would be 0.
Correct. Vertical would be 0.
And horizontal would still be 350.
Good. Horizontal is just 350. Very good. Thank you. All right, C. What's the horizontal component of the velocity just before hitting the ground? Zach.
0.
Just before. Not 0. That would be just after in either direction, I guess.
Would it still be 350?
It would still be 350. Good. Last one. If the airplane speed were instead 450 kilometers per hour, would the time of fall be larger, smaller, or the same?
The same.
The same. Very good, because we're not affecting any vertical information there. All right, and last but not least, Connor. You got number 9. Number 9 says you got 3 paths for kicked football. Ignoring the effects of air on the flight, rank the paths according to A, the time of flight, B, the initial vertical velocity component, and C, initial horizontal velocity component, and D, initial speed. All right, let's actually start with C, because I think that one's easiest. Connor, which of those 3 kicked footballs must have the greatest initial horizontal velocity component? C, clearly C, because they went the farthest horizontally. How about initial vertical velocity component? That's question B.
A.
Why? Did it go up higher?
Well, no. They would all be the same.
They're actually all the same. So this is a little bit different than Emily's question. These don't have the same kick speed. Because if they did, you would think A would have the greater time because it was kicked at a steeper angle. But no, they're actually, for whatever reason, all have the same vertical component of velocity because they all go up the same vertical distance. Okay, so that said, let's go back to A. Which one's got the longest time of flight? Careful here.
I would say C.
Because it went the farthest?
Yeah, but I mean, in a way, it would, if I'm not mistaken, it would be C, because since they're all going the same height, it wouldn't, if it goes farther, it would be in the air longer, in my opinion. Or you might be wrong.
Yeah, not necessarily. Same with like dropping the bullet and firing the bullet. Yeah, the one you fire is, much farther away.
So it would all be the same.
But the fall time's the same. So if the vertical information is the same, that the time is actually all the same. Which would only be true if they all had different kick speeds, different launch speeds. It's not the same question we gave Emily. Okay, so we said the vertical component's all the same. The horizontal components are different, so which one must have been kicked with the greatest initial speed overall? C. Most of that speed was horizontal, or more of that speed was horizontal and vertical, but C must have the greatest. All right, number 11. You are driving directly behind a pickup truck going at the same speed as the truck. A crate falls from the bed of the truck to the road. In years past, we had a little trouble imagining this, so pretend, for the sake of this problem, I'm better at drawing trucks. Does that look like a duck also? Pretend the tailgate is down and the box is just sitting on the tailgate, and for whatever reason the tailgate just falls off. It's not that somebody like kicked it out of the truck, it just falls off. And our truck is moving. So, a crate falls from the bed of the truck to the road, and you're driving directly behind it. Okay, so A, will your car hit the crate before the crate hits the road? If you neither brake nor swerve. Marcella. So let me draw you in your car. You're tailgating a little bit, which is dangerous. You shouldn't do that. Okay, so what's going to happen? You're going to hit this crate? Well, yeah, you're going to hit it, but are you going to hit it before it hits the ground? And like, shouldn't you know how fast you're going? Doesn't matter. Why? Because even though Marcella is tailgating, there is still a gap here. There's some distance between the truck and the car. So if this crate just falls, randomly hits the ground.
Do we know how high up
Is the blue car still moving forward?
Yeah, you guys both going, let's say 50 miles an hour. Eventually you'll run over the crate, I understand that. But will you hit the crate before the crate hits the ground? That's the question. No. Why? It's not about this distance versus this distance. Because even if you were super tailgating, I just like an excuse to draw, I guess. Now you have a bit of a station wagon. Even if you were super tailgating inches away from the bed of that truck and the crate falls.
The crate is still going 50 miles an hour.
Yeah.
So
Now,
it's still going to keep.
What may affect this though is air resistance. So of course we have to ignore air resistance. That always doesn't matter for us. But of course it does matter in real life. You ever stuck your hand out of a car moving 50 miles an hour? I mean, you can feel that. There's significant air resistance there. But ignoring air resistance, this box is also moving forward at 50 miles per hour. So it will continue moving forward as it falls. So even though it's falling, it's still moving this way. So
That's the same thing with the whole up in the air with the train.
somebody, to the ground would see the crate doing that. They would still see it going forward and down. not just straight down. So even if you're super tailgating, you wouldn't hit the crate and you wouldn't have to swerve, well, before it hit the ground. All right, Marcella, during the fall, is the horizontal speed of the crate more than, less than, or the same as the truck if we ignore air? The same. Okay, and maybe we should answer that part first. Yeah.
What if say you're in the train and you throw the ball up and you don't catch the ball and it hits the ground? It hits the ground, the bed of the train car. Is it still moving at the train speed, or
You throw it straight up and you don't catch it?
Yeah.
you don't catch it? It just hits the train's
Pulling the train.
Oh.
the train car.
Well, if you throw it up, it has whatever horizontal speed you originally had. So if that were 50 miles an hour, it would have 50 mile an hour horizontal speed. If you pay attention to where it lands, like does it land behind you, does it land in front of you,
just throw it
you would
straight
know.
down. And it just-
Then yeah, that means you are accelerating, but the ball wasn't. As soon as you let it go, it wasn't anyway. And then you can figure out if you're slowing down or speeding up.
But you could really
But you
slow down the speed.
would probably feel that too. All right, number 12, next one, Daniel. All right, is it possible to be accelerating while traveling at a constant speed? Yes, such as?
Like circular.
Exactly. If you're moving in a circle, you could be going at 50 miles an hour at a set speed, but you have to be accelerating if you're changing direction. All right, Daniel. Okay, is it possible to round a curve with zero acceleration? No. You have to have an acceleration if you're changing direction. That's a definition of acceleration. It is change in velocity over time. Is it possible to round a curve, Daniel, with a constant magnitude of acceleration?
Yeah.
Sure. Obviously, the direction of acceleration will constantly be changing because it's center seeking. But yeah, the magnitude could be the same. If it's v squared over r, and the v is staying the same and the r is staying the same. All right, 13, Zach. Oh, it's your question. Well, while riding in a moving car, you toss an egg directly upward. Does the egg tend to land behind you, in front of you, or back in your hands if the car is traveling at a constant speed?
If it's traveling at a constant speed, it lands back in your hands.
Good. Right back in your hand if it's traveling at a constant speed, because the egg has the same horizontal velocity that you have. B, now what if you are going faster, or what if you are accelerating, speeding up? Exactly. Because it's like you moved out from underneath the egg. You throw the egg up, but if you're gaining speed and the egg is not, it's going to be behind you. Very good. And then what if you were slowing down? Yeah. Then you're slowing down, but the egg is not, so it would land in front of you. Very good. How amazing that that was your question. Connor, 14. Okay, a passenger in an elevator drops a coin while the elevator descends at constant speed. According to A, the passenger, and B, someone waiting on the next floor, is the acceleration of the coin equal to, less than, or more than G? So somebody is in an elevator, but it says at a constant speed. They're moving in an elevator at a constant speed, so somewhere in the middle of the travel, and they drop a penny. What acceleration would the person in the elevator measure for the coin? They would measure gravity. What acceleration would somebody standing on the second floor looking in observe if it was like a glass elevator?
They observe the speed that the elevator is traveling along with gravity.
So you think it would be faster than gravity?
It would, but it'd be faster from their perspective, but it's not true to be faster.
You're right. They're going to measure a faster fall speed for the penny than somebody in the elevator. But my question isn't about speed. It's about the rate of change of speed. It's about the acceleration they would see.
Then it would be gravity, measure gravity.
It would also be gravity.
That's the whole thing of
The bar.
the velocity of the acceleration is the same.
Yeah. They're measuring different velocities, that's true. But the rate of change is still the same regardless if you're in the elevator or if you're on the second floor looking in. Is that your question?
No, but my question is
Okay then.
Is that like similar to, well, it's a little bit different because whenever, I've done this multiple times, on like a free fall type of
Ride?
amusement park,
Yeah.
penny,
Yeah.
and you make it down to what penny does.
So what would that mean about your acceleration versus a penny?
It's greater acceleration.
Yeah. Some of those rides pull you down faster than free fall. So like you can set the penny on your knee and you just
It's like
fall underneath it. Yeah. Yes.
actually, if you're at level, and I feel like it's not ever something with acceleration, why is it?
Yes. And that's actually getting into our universal gravitation unit. Do you know which one would be less?
Probably mountains.
Yes. Because when we study universal gravitation, the amount of gravity you have towards an object, any object like you towards the Earth, is based on the mass. So that wouldn't necessarily change, but the distance you are away from that center of mass. So if you're on Mount Everest, you have a much greater distance away. So you would technically weigh less.
Is the center of mass the core? The center of
It's the point where you could consider all the mass to be located. Which is yet another topic we'll study. All right, our last question. Maybe actually finish one period. Our last question is 15, before the bell rings on us. All right, a pickpocket is standing on the rear observation platform of a train moving with a constant velocity and drops a wallet over the rear guardrail. Thomas, this one's for you. Let me sketch this out for you. Or not. All right, I've got a red caboose. A little platform. I am drawing trains. Okay, so here's our little platform. Here's our pickpocket. Here's the wallet. Here's Thomas. Okay. Okay, so a pickpocket drops the wallet over the edge of a moving train. Describe the path of the wallet as seen by the pickpocket. So as seen by this person, what will they observe for the wallet?
Just jumping this way.
Thomas. You ruined my video, Brandon.
The train's moving this way?
Train's moving this way. If you're the pickpocket, you're just dropping it. What do you see? How does the wallet move relative to you?
I guess you think going away from it, so it seems like it's going away.
You are moving away from the drop point. But does that mean the wallet, this is like the crate thing.
Well, it still seems like it's going straight down.
Yeah, to you on the train, you drop it, imagine you can't see the ground because that of course would mess with your perception, but to you, the pickpocket, it would appear to go straight down because it has the same horizontal velocity that you do. What would it look like to the accomplice over here on the ground? What would the wallet look like to them?
You go like the direction of the train towards the ground.
Exactly. It's still moving forward, according to this person in blue. Of course, falling, but it is still moving forward because it had that horizontal velocity. And lastly, relative to a police officer on another train, moving in the opposite direction. So here's the cop train going this way. How does this cop see the wallet? Or how is it different than this picture?
I thought it'd be the straight down.
More. It'd be the same, but it would appear to have even more horizontal acceleration. Okay, well, I spoke too soon.